Now I am moving into the last part of module 5 continuous time Markov chain. In this I am going to discuss the simulation of queuing systems. So, the module 5 continuous time Markov chain started with the definition and the properties and so on. Then I discussed the birth death process. Then I discussed the application of a birth death process in simple Markovian queuing models. Then also I have discussed the queuing networks, that is also a multidimensional continuous time Markov chain as application. And finally, I have given few practical application in cellular networks for the performance analysis. Now I am going to discuss the discrete event simulation of a simple Markovian queuing systems. So, in this queuing network modeling lab, one can do discrete event simulation, and the discrete event simulation for the queuing network involves Markovian queues. We can do some experiment over the Markovian queues, and we can do the discrete event simulation for the non-Markovian queues, and one can do the discrete event simulation for the queuing network also, and finally one can do the fluid queues also, one can simulate. But since I have discussed only continuous time Markov chain till now, I am going to do a discrete event simulation for the Markovian queues. So, that is in the first 3 experiments. The other 3 experiments are related to the non-Markovian queues. The first experiment consists of a simulation of a MM1 queue, single server queue, and a MMC finite server queues, and the infinite server queue. So, in the sometime I have done the discrete event simulation of a MM1 queue. So, let me go for MMC finite server queue. So, in these you need the input of arrival rate, input of the departure rate, and the number of servers. It is a multi-server infinite capacity model. So, suppose you choose the arrival rate is 2 and the service rate is 3 and the number of servers are 2. That means it is a MM to infinity model with the arrival rate 2 and the service rate is 3. So, one can start the discrete event simulation by clicking the start. Then you will get the window of so this is the sample path over the time, what is the system size. So, at this time point 1 arrival comes, then 2, then service is completed and so on. So, this is the sample path over the time, and here you can get the performance measures. So, whatever I have discussed the performance measures of a steady state distribution and all other performance measures, one can get it with the theoretical results in the third column, whereas the second column gives the running time till the discrete event simulation runs for 15 time unit, and what is the result for the mean number of systems and so on, and this will converge to this value for t tends to infinity. So, I make sure that this arrival and departure rates are satisfying the condition, so that the steady state distribution exists. Therefore, as a t tends to infinity, this will reaches the steady state theoretical result. If you change the value arrival rate and the departure rate something else, then there is a possibility if the conditions for the stationary distributions are not satisfied, then still the runtime results you will get, but that will not be converged to the theoretical, and also the steady state results will not be possible. It will be a dash here. So, as long as the steady state distribution those conditions are satisfied, then you will have the results in the third column, otherwise you will not have the results here. So, now you can see the throughput till this much time you are getting 2.0, whereas the steady state throughput is 2. Throughput is nothing but the number of customers served per unit time. Like that one can get the throughput utilization, average response time or mean sojourn time, and mean waiting time in the queue. So, using Little's formula used to find out this quantity. So, this quantity you can get it from the discrete event simulation at any time as well as the theoretical result, and this is the mean number of customers in the system, that is E n, and the mean number of customers in the queue, that is EQ, which we got it. So, this result one can see the discrete event simulation as well as a t tends to infinity, what is the theoretical result if the conditions for the stationary distribution satisfied. And here this information is how many calls are entered, how many customers enter into the system, and how many are served, and how many customers are blocked. Here there is no blocking because it is an infinite capacity system, and we are considering the retrial orbit and so on. Therefore, here it says number of orbit customers is 0, but this is not necessary. This is irrelevant information in the MMC queuing model. Now, let me go back and do the live simulation of MM infinity. So, here you have to provide only the arrival rate and the service rate, because the number of servers are infinite. It's a self-service system. You can cross check the theoretical results are correct and so on. So, here I am getting the steady state result based on the theory, whereas this is the runtime results. There is no blocking probability because the system infinite capacity. Mean number of customers in the queue, that is 0, and here also 0 because it is a infinite server. Therefore, who customers who enter into the system immediately will get the service. Therefore, the queue average number of customers in the queue, that is 0, and the average time spending in the queue, that is also 0. That is correct. There is no blocking, and utilization is what is the probability that the servers are utilized. Now, let me go to the next experiment, that is second experiment for the finite capacity queuing model, whereas the first experiment is the infinite capacity queuing model. So, in this we have we need to give the arrival rate, service rate, and the number of servers. You can go for the multi-server MMCN model. You can give one also. You can give infinite servers also one can give. So, here the number of servers, suppose you fix it 3 and the capacity is 4, you can do the simulation. So, the blocking probability in the runtime, there is at this time it does not cross the number 4. Therefore, the blocking probability is 0 in the runtime result, whereas the theoretical steady state result says the blocking probability is 0.005. So, whenever the system touches 5, then you will have the blocking probability in the runtime. So, this is a discrete event simulation. See, number of customers blocked is till now 0. Therefore, you are getting the blocking probability 0 at this runtime. Suppose you run it again. Let us see. Now, also it does not crosses the system size by 2. So, maybe I can reset with the number of servers. I can put 2 and the capacity is 3. So, the blocking probability is this much. The capacity of the system so there is no arrival after crossing, therefore still you are getting the blocking probability is 0, whereas the steady state theoretical result says 0.037. So, one can simulate with the different parameters, and you can see the sample path. So, this is the sample path for MM 2-3 queuing system with the arrival rate 2 and the service rate is 3. Yeah, now we are getting the blocking probability because the system crosses, touches the capacity 3, therefore, some calls are blocked, some customers are blocked, therefore, the blocking. So, you can find out from here. Number of customers 44 entered and 4 are blocked, therefore, that ratio will be the blocking probability because it is a discrete event simulation. Now, let me go back and go to the experiment 3. Experiment 3, we have a retrial model with the bulk arrival and bulk service. So, now it is no more a birth death process simulation, this is a non birth death process because you have a bulk arrival and a bulk service was possible and a retrial. Therefore, let me show the simulation. You need some more information. So, what is the arrival rate you have to supply? Suppose if it is a bulk arrival, then you should say what is the distribution, whether the bulk arrival comes in a bulk some constant number or it comes in a some distribution. You can choose it is geometrically distributed, and the parameter for the bulk arrival parameter you can choose some 0.5. Then the departure rate, you can choose the departure rate. It can be a bulk departure or bulk. So, either you can choose a bulk arrival or bulk departure, or you can choose both also. The number of servers in the system, suppose there are 2 servers in the system and the capacity system is 4, or you can choose a infinite capacity of the system also, and if you need a orbit, then you have to click for orbit, and if you are changing the queuing discipline, the first come first served, last come first served or random order, you can choose the queuing discipline also, accordingly the discrete event simulation goes. So, this is not a birth death process, this is a continuous time Markov chain simulation. With a different queuing discipline also one can go for it. Now, once you start the simulation, yeah, since it is a bulk, we have made a bulk arrival, whereas we made it, we did not click for the departure, bulk departure, therefore, the customers keep going by one whenever the service is over, but since it is a bulk arrival with the arrival distribution is the number of arrivals that is geometrically distributed, therefore, it just jump with the bulk arrival, whereas the departure is by one. And here is the performance measures, is the runtime performance measures, and we did not till now we did not supply the theoretical steady state or theoretical results for this model. And these are all the different results in the over the runtime. And similarly, one can go with the bulk departure, and we can change the queuing discipline also. So, this is a discrete event simulation sample path for this scenario. So, I can reset, and if I do not want the bulk arrival, and if I choose the capacity of the system is 4. So, this will be a no bulk arrival, no bulk departure, therefore, this is a MM 2-4 system with the first come first out, and I can go for instead of first come first out, I can go for the last come first out also. The customer is last entered, he is getting the service first. So, this is a steady state and this is a time dependent result, and I can change again this into inf. That means it is a 2 servers infinite capacity model with the first come first served. Still this is in the testing phase, so some of the things should be removed, some of the things has to be edited, so still it is in the testing phase. So this is the performance measures for the MM2 infinity model. So that means in this experiment also you can remove the bulk arrival and the bulk departure part and so on. You can try the simplest simple Markovian queuing model also. One can do the discrete event simulation of that. And since it is an infinite capacity model, the blocking probability is 0. And the steady state throughput is 2, one can find out from the formula also. Whereas the runtime is this. So if this discrete event simulation runs for a longer time, then this will converge to 2. Like that you can discuss the all other results also. All the results will be converges to the steady state theoretical probability, the theoretical results. So with this let me complete the discrete event simulation of a simple Markovian queuing model, because we are discussing this under the title of application of a continuous time Markov chain. Therefore, I discuss only the Markovian queues. There are some non-Markovian queues and so on. So I am not discussing the non-Markovian queues at this stage. After I discuss the renewal theorem and the Markov regenerative process and SME Markov process and so on, I will be discussing the non-Markovian queuing systems also. So here we have discussed only the simple Markovian queuing system, that is nothing but the applications of a continuous time Markov chain. As a summary, the last 7 lectures we have discussed the continuous time Markov chain from the definition and properties and a few simple continuous time Markov chain, starting with the Poisson process, birth-death process, pure birth process, pure death process, then application of CTMC in the queuing model, starting with the MM1 queue and other simple Markovian queues. Then we discuss a few queuing network which has the product form solution. Then in the last this lecture we have discussed the applications of CTMC in 2G second generation cellular networks as well as the third generation cellular networks. And application of CTMC in the 2G networks is the birth-death process, whereas the applications of CTMC in 3G cellular networks is the quasi-birth-death process. Even though I have not discussed in detail the complete modeling, one can see it from that paper. My intention here is explain the quasi-birth-death process through the applications. And we discuss the stationary distribution and all other performance measures for the birth-death process comes in the second generation networks and the quasi-birth-death process in the third generation networks. And finally, I have given the discrete event simulation for simple Markovian queuing systems only. There are some more non-Markovian queuing systems, so that I will be discuss in the other models. The references are Grossenari's book and Mehdi book, Kishore Trivedi's book. Thanks.